Our galaxy was built from the ruins of others. The Milky Way you see on a clear night is not a pristine creation, but the product of violent galactic mergers, a cosmic history written in starlight and scars. By the end of this video, you will understand how cataclysmic collisions forged our celestial home, transforming your view of the night sky forever. We will uncover how our galaxy's spiral arms and central bulge are relics of ancient battles, and what the ghosts of consumed galaxies can tell us about our own origins. What does it mean to live in a universe where creation requires destruction? That primordial darkness was not empty, but pregnant with potential. After the immense heat of the Big Bang began to fade, the universe entered a deep cosmic night, a period lasting hundreds of millions of years where not a single star shone. The cosmos was a vast, opaque sea of hydrogen and helium gas, so dense that light could not travel freely. Yet within this formless void, an invisible architect was already at work. Dark matter, a substance we still struggle to understand, began to clump together under its own gravity. These clumps acted as cosmic seeds, creating invisible wells of gravity scattered throughout the expanding universe. Think of these gravitational wells as gentle dips in the fabric of space, subtle pockets where matter could slowly accumulate. The primordial gas, swirling in the darkness, was gradually drawn into these pockets. Over eons, these clouds of gas grew denser and hotter under the relentless pull of gravity. The pressure and temperature at their cores eventually crossed a critical threshold, triggering a miracle of physics. Deep within those darknesses, the first stars ignited. Their birth was a violent, brilliant flash that tore through the cosmic gloom. These first stars were not like our sun. They were behemoths, hundreds of times more massive, burning ferociously bright and living fast, dramatic lives. Their endings were just as spectacular. Within only a few million years, they exhausted their fuel and exploded in colossal supernovas, cataclysmic events that forged the first heavy elements and blasted them out into the void. The iron in your blood and the calcium in your bones were forged in the hearts of those first, long-dead stars. This cycle of star birth and death, playing out again and again, enriched the cosmic gas, transforming it from a simple soup of hydrogen and helium into a more complex brew capable of forming rocky planets and eventually us. These slight density fluctuations, those first tiny seeds of dark matter, were the blueprints for everything we see today. From those humble beginnings, the first small galaxies began to coalesce, swirling in the darkness. The stage was now set. The primordial actors had taken their places, and the drama of construction through destruction was ready to begin. About 10 billion years ago, our peaceful Milky Way was shattered by a cosmic intruder. A smaller galaxy, now known to astronomers as Gaia-Sausage-Enceladus, did not simply drift into ours. It slammed directly into the heart of our young galaxy in a head-on collision of staggering violence. This was not a gentle dance of stars passing in the night. It was a frontal assault that sent shockwaves through the very fabric of our galactic home. The orderly disk of the Milky Way was thrown into chaos, its stars sent reeling onto wild, new paths. The Intruder galaxy itself was torn asunder, its stars shredded and scattered. Today, we can still see the ghost of this impact, not in a shape in the sky, but in the motion of stars. When scientists map the velocities of millions of stars, they find a distinct pattern, a sausage-shaped structure in this abstract space of movement. These are the stellar survivors of that ancient wreck, still moving on the radical, plunging orbits they were thrown onto during the merger. The legacy of this violent encounter is written into the very body of our galaxy. It is credited with building a large part of the Milky Way's thick disk, that diffuse band of older stars that surrounds the brighter thin disk, and contributing a vast number of stars to our galaxy's inner halo. In one fateful impact, the Gaia-Sausage-Enceladus galaxy donated a huge amount of its mass and a distinct chemical signature, permanently altering the Milky Way's composition and destiny. It was a brutal act of cosmic cannibalism that ultimately made our galaxy bigger, thicker, and more complex. This foundational merger proved a simple, stark rule of the cosmos. Growth comes from consumption, and this was only the first course in a long galactic feast. The aftermath of that ancient collision left behind more than just a thicker disk. It scattered a population of stellar survivors into a vast, spherical cloud that surrounds our entire galaxy. This is the galactic halo, a silent, diffuse museum of celestial archaeology. Within this halo, the ghosts of consumed galaxies drift in plain sight. To find them, astronomers act as stellar detectives, reading the subtle clues written into starlight itself. They measure not just a star's position, but its motion through space and, most importantly, its unique chemical fingerprint. Stars that form together in the same small galaxy share a distinct chemical composition, like a family sharing a specific genetic marker. This cosmic DNA allows scientists to identify stars that originated in the same place, even after their parent galaxy has been completely shredded and its stars scattered across thousands of light years. The result is a breathtaking cosmic map. Wrapped around the Milky Way are faint rivers of stars, stellar streams that trace the orbital paths of long-dead galaxies. Each stream is a chapter from a different merger event, a narrative thread in our galaxy's violent biography. By patiently reconstructing these stories, astronomers are piecing together a family tree of the Milky Way, identifying the dozens of smaller galaxies it has consumed over billions of years. It is a biography written not in ink, but in the ancient light of stellar fossils. But the stars themselves are merely the visible actors in this cosmic play. They move across a stage set by an invisible director, a substance that remains one of the greatest mysteries in all of science, dark matter. Every galaxy, including our own, is cocooned within an immense, unseen sphere of this enigmatic material. It emits no light, it reflects nothing, and it passes through ordinary matter as if it were not even there. Yet its gravitational influence is absolute. Think of a galaxy's dark matter halo as a deep, invisible gravitational well, a pit in the fabric of space whose walls are made of pure gravity. When two galaxies drift near one another, their dark matter halos are the first to touch. These vast, unseen structures begin to intertwine, their gravitational forces creating a complex, shifting framework. This is the true beginning of a merger. Long before the stars of one galaxy begin to feel the direct pull of the other, their paths are already being bent and twisted by this unseen gravitational handshake. The chaotic dance of the stars we see is choreographed entirely by forces we cannot see. The final shape of the Milky Way's dark matter halo is therefore a living record of its violent past. It is not a smooth, perfect sphere. Instead, it is a lumpy, complex structure, its form built from the accumulated dark matter of every smaller galaxy it has ever consumed. Each merger left behind an invisible scar, a subtle density fluctuation in the halo that permanently altered its gravitational landscape. So, when we ask what truly builds a galaxy, the answer lies not just in the brilliant stars, but in the profound darkness that binds them. This invisible architecture governs the fate of everything we can see. It guided the ancient collision with the Gaia-Sausage galaxy, and it continues to orchestrate the slow, inevitable mergers happening even now. Our galaxy's past was written by this unseen hand. What then does its future hold? The true violence of a galactic collision unfolds with an almost serene slowness. It is a car crash lasting hundreds of millions of years. As two galaxies first draw near, their gravitational embrace begins a profound and destructive metamorphosis. They do not simply bump into one another. Instead, their mutual gravity acts like an immense, invisible hand, stretching and pulling each galaxy apart. This process, known as tidal stripping, wrenches long, shimmering tails of stars and gas from their galactic homes, painting luminous bridges across the void. These stellar streams are the first visible scars of the encounter. While the image of stars smashing together seems intuitive, the reality is far stranger. The distances between individual stars are so astronomically vast that direct collisions are extraordinarily rare. The real chaos is not in impacts, but in orbital disruption. The gravitational turmoil completely scrambles the predictable paths of billions of stars, throwing them onto new, often chaotic trajectories. This gravitational sculpting creates breathtaking new structures within the merging galaxies. Astronomers observe vast, concentric shells of stars like ripples frozen in time, echoing out from the galactic center. They find warped disks bent out of shape by the gravitational tides and brilliant rings of newborn stars. The real fireworks, however, come from the gas. Unlike stars, the immense clouds of interstellar gas and dust do physically slam together. These violent compressions trigger ferocious waves of star formation, known as starbursts. The merger ignites countless new suns in a brilliant, short-lived blaze of cosmic creation. The original identities of the two galaxies are systematically erased. Their distinct shapes are lost, their stars scattered, and their gas consumed in a final burst of stellar birth. What emerges from this billion-year-long dance is something entirely new, a single, more massive galaxy. This is the ultimate testament to gravity's power, not just to destroy, but to completely transform. Rising from the galactic plane like a dense, cosmic fortress, the central bulge of the Milky Way holds a violent secret. That bright, peanut-shaped core of ancient stars is not a serene retirement home for old suns. It is a monument to chaos, a structure whose very form was forged in the heat of ancient collisions. While some parts of a galaxy evolve in relative isolation, a galactic bulge of this shape often tells a different story. It speaks of a rapid, violent construction, a period when vast rivers of gas and countless stars were violently funneled inward by the immense gravitational tides of a merger. The orderly orbits of these stars were completely scrambled, forced into new, radical paths that weave above and below the galactic center. It is this chaotic dance, this gravitational turmoil frozen in time, that gives the bulge its distinct boxy or peanut-like appearance when viewed from certain angles. This structure is far more than a simple collection of stars. It is a living archive. The types of stars found there, their ages, and their chemical compositions are all clues. They encode a detailed history telling astronomers not just that a merger happened, but approximately when it occurred and how violent the event truly was. The ancient, metal-poor stars might be refugees from a long-devoured companion galaxy, while others could be native stars thrown into the chaos. So, the next time you see an image of our galaxy's brilliant heart, remember you are not just looking at a dense cluster of light. You are looking at the permanent scar of a foundational trauma, the enduring legacy of the violent mergers that built the very center of our celestial home. Our galaxy's disk is actually two disks in one. Nestled within the bright, familiar band of the Milky Way lies a hidden structure, a thicker, more diffuse layer of ancient stars that envelops the thin disk like a soft cosmic halo. This is the galactic thick disk, and its existence is a direct testament to a past of profound violence. The stars that call this region home are different. They are older, and they possess fewer of the heavy elements that are abundant in younger stars like our Sun. They also move on more radical, plunging orbits, diving through the thin disk and soaring high above the galactic plane. How did this distinct population of stars get there? The answer lies in a gravitational stir of cosmic proportions. When the Gaia-Sausage-Enceladus galaxy slammed into the infant Milky Way, it did not just add its own stars. The immense energy of the collision sent powerful shockwaves through our galaxy's pre-existing thin disk. This was not a gentle mixing. It was a violent churning, a gravitational upheaval that heated the disk and flung countless stars onto these new, higher, and more erratic paths. In essence, the impact puffed up the galaxy, scattering stars upward and outward to form this new, thicker layer. This process did more than just change where stars lived. It permanently mingled two distinct stellar populations. The Intruder galaxy contributed its own metal-poor stars, while the native Milky Way stars were thrown into the chaos. Their once orderly orbits scrambled forever. The thick disk we observe today is the fossilized record of that stellar stir. It is a permanent layer of complexity in our galaxy's structure, a direct result of a chaotic impact that ultimately created a new form of order. This reveals a deeper truth about cosmic evolution. The most enduring structures are often born not from quiet isolation, but from the fiery turmoil of a collision. Orbiting our galaxy like distant, glittering islands are some of the oldest structures in the universe, globular clusters. These dense spheres, each containing hundreds of thousands of ancient stars, are more than just beautiful relics. They are captured treasures, celestial souvenirs brought home from the Milky Way's violent feasts. Many of these clusters did not originate here. Instead, they were hitchhikers, ripped from the grasp of smaller dwarf galaxies during those long-ago mergers. Their incredible density is their saving grace. While an entire galaxy can be torn apart by gravitational tides, a globular cluster is so tightly bound that it can pass through the chaos of a merger completely intact. It emerges from the destruction as a single, brilliant unit, a surviving piece of its original home. This resilience makes them perfect cosmic tags for astronomers. By reading the subtle signatures within their starlight, their precise ages and unique chemical compositions, scientists can trace their lineage. A cluster with a distinct chemical fingerprint, different from the native Milky Way population, is a clear indicator of an external origin. Its very presence tells a story of capture. Even the path it follows, its orbit around the galactic center, can be a clue, tracing back to the specific merger that delivered it. So each of these glittering swarms is a trophy, a prize collected by our galaxy in its long history of cosmic battles. They are not random collections of stars, but enduring markers of identity, each one a brilliant, surviving witness to a galaxy that no longer exists. Even now, the Milky Way is not at rest. It is actively consuming a smaller companion, a cosmic snack that provides a living demonstration of its violent methods. The Sagittarius dwarf spheroidal galaxy is a small satellite that has been orbiting our own for billions of years. With each close pass, it pays a terrible gravitational toll. The Milky Way's immense tidal forces, the same kind of stretching pull the Moon exerts on Earth's oceans but on a galactic scale, relentlessly tear the dwarf galaxy apart. They strip away its stars, pulling them out into long, shimmering rivers of light. These stellar streams now form a vast, faint loop that wraps around our entire galaxy, a delicate cosmic braid slowly being unwound and absorbed. This is tidal disruption happening in real time, a process we can observe and measure. offering a front-row seat to the same mechanisms that built our galactic halo from the ruins of others. But the influence of this ongoing merger is not confined to the distant halo. As the core of the Sagittarius dwarf plunges through the outer reaches of our galaxy's disk, its gravity creates ripples. Think of it like a stone dropped into the serene pond of the Milky Way, sending waves of density through the gas. These ripples can trigger the collapse of gas clouds, potentially sparking new episodes of star formation. We are witnessing a small-scale version of the chaotic creativity that the larger mergers of the past must have produced. The Sagittarius stream is more than a beautiful astronomical curiosity. It is a living laboratory, a dynamic model that allows us to watch, in extreme slow motion, the very processes that forged our galactic home over billions of years. These stellar streams are the galaxy's final, dissolving ghosts. They are ethereal rivers of stars, far too faint to see with the naked eye, yet they wrap around our entire Milky Way in vast, delicate loops. Each stream is a celestial autopsy, the final remains of a star cluster or a small galaxy that ventured too close and was torn apart by our galaxy's immense gravity. The process is relentless but slow. Over billions of years, tidal forces stretch the object out, pulling its stars into a long, shimmering ribbon that traces the exact path of its orbit around the galactic center. This is how a dwarf galaxy dies, not with a bang, but with a long, silent unraveling. Astronomers have become cosmic cartographers of these apparitions, giving them haunting names like the GD1 stream, the Orphan stream, and the Gellum stream. Each name marks a different victim and a separate chapter of cosmic history. The GD1 stream is a particularly pristine example, a long, thin line of stars that seems almost too perfectly placed, a clean scar from an ancient disruption. The Orphan stream tells a more complex tale, possibly the last remnant of a dwarf galaxy that was one of the Milky Way's very first meals. By simply mapping the positions and motions of the stars within these streams, scientists can rewind the clock. They can trace the stream backward along its orbital path to identify the original object, the progenitor that was consumed. It is a form of celestial genealogy, allowing us to count the Milky Way's victims and understand the sequence of its growth. But these streams offer an even deeper revelation. Their very shapes are exquisitely sensitive to gravity's subtle touch. As a stream of stars winds its way around the galaxy, its path is not perfectly smooth. It develops kinks and gaps, subtle warps and bends. What could possibly cause such distortions in a river of stars? The answer lies in the invisible landscape of dark matter. Astronomers theorize that these ripples are caused by gravitational tugs from unseen clumps of dark matter, substructures hidden within the galaxy's vast halo. The streams act like cosmic fishing lines, their twists and turns revealing the size and location of the dark matter that tugs on them. By studying the ghosts of galaxies past, we are therefore mapping the invisible architecture of the present. These faint stellar rivers provide a detailed timeline of our galaxy's assembly. They are not random debris, but structured narratives. A dense, concentrated stream might be from a recently disrupted globular cluster, while a broader, more massive river could be the final breath of a substantial dwarf galaxy. Each one has a different age, a different chemical composition, and a different story to tell. Together, they form a grand chronology, a living history book written in starlight, detailing the violent, creative, and ongoing process that built our home in the cosmos. The same gravitational rules that built our galaxy from the ruins of others will one day seal its fate. In approximately 4.5 billion years, the Milky Way will begin its final, most spectacular merger. Our nearest large galactic neighbor, the Andromeda galaxy, is currently hurtling toward us through the void. This is not a possibility but a certainty, a direct collision course set by the relentless pull of gravity. When this cosmic dance begins, the two majestic spiral structures we see today will be torn apart. Their orderly disks of stars, gas, and dust will be thrown into utter chaos. Computer simulations of this event paint a breathtaking picture. The galaxies will not simply pass through one another. They will swing past in a close encounter, their gravitational forces stretching long, brilliant tails of stars into space before falling back together in a final, embracing merger. The familiar spiral arms of both the Milky Way and Andromeda will be completely erased, their distinct shapes lost forever. What will emerge from this billion-year-long turmoil is something entirely new and, to our current eyes, alien. The two spiral galaxies will combine to form a single, giant elliptical galaxy. Astronomers have already given this future colossus a name, Andromeda. This new galaxy will be a vast, featureless sphere of stars, a celestial beehive where suns orbit in every direction without a central disk. The night sky from a world within Andromeda would be utterly transformed. Instead of a faint, milky band arching overhead, the sky would be uniformly filled with stars, a dazzling, three-dimensional cloud of light with no recognizable structure. This epic future event is a perfect mirror to our galaxy's violent past. The processes that shredded the Gaia-Sausage-Galaxy and built our thick disk are the very same forces that will one day dismantle the Milky Way itself. It is a powerful reminder that in the cosmos, no structure, no matter how grand, is permanent. The universe is in a constant, dynamic state of evolution, where creation and destruction are two sides of the same cosmic coin. At the very center of this cosmic violence sits a silent, gravitational anchor. Our galaxy, like most other large ones, hosts a supermassive black hole named Sagittarius, a star. This colossal entity is not a passive bystander in the drama of galactic collisions. It is a central actor, a gravitational engine whose own history is written in the mergers the Milky Way has endured. When two galaxies collide, their central black holes are carried along with the flow of stars and gas. They do not immediately plunge together. Instead, they begin a slow, cosmic dance toward the center of the newly formed galaxy, a process driven by a phenomenon known as dynamical friction. As these black holes move through the dense stellar environment, their immense gravity perturbs the orbits of surrounding stars, creating a gravitational drag that steadily slows them down. This friction acts like a cosmic brake, causing the black holes to lose energy and spiral inward over millions of years. Eventually, they find each other, forming a binary pair, a tight, whirling dance of two gravitational titans locked in a mutual orbit. This binary partnership is far from peaceful. Their orbital energy is so vast that it violently stirs the surrounding reservoir of gas and dust. This chaotic heating effect can prevent the gas from cooling and collapsing to form new stars. In some of the most massive galaxy mergers, this process can effectively shut down star formation in an event astronomers call quenching. The galaxy, once a vibrant stellar nursery, can be transformed into a quiet, aging collection of stars, its creative potential stifled by the turmoil at its heart. The final act of this billion-year-long dance is the most energetic event in the universe since the Big Bang. When the two black holes finally merge, they release a cataclysmic burst of gravitational waves, ripples in the very fabric of space-time itself. These waves carry away an amount of energy equivalent to the light of trillions of suns, all emitted in a fraction of a second. The mass of our own Sagittarius, a star, is therefore a living record. It is the sum total of all the smaller black holes it has ever consumed, a direct testament to the number of galactic cores our Milky Way has devoured. This dark heart is the ultimate witness, a silent keeper of the galaxy's most violent secrets. A star's light is more than just brightness, it is a detailed chemical biography. Every sun carries within its spectrum a unique fingerprint, a precise record of the specific cosmic ingredients present in the cloud of gas where it was born. This is the galactic equivalent of DNA, an immutable signature that persists for billions of years. When our Milky Way consumes a smaller galaxy, it does not just acquire new stars, it imports an entire chemical library. The native stars of the Milky Way, like our own sun, are relatively rich in heavy elements forged in the hearts of successive generations of stars, but many of the smaller galaxies consumed by our own were ancient and stunted in their growth. They lack the vigorous, ongoing star formation needed to enrich their gas with these heavier elements. Their stars are metal-poor, meaning they possess far smaller amounts of elements heavier than hydrogen and helium. When astronomers point their spectrographs at millions of individual stars, they are reading these chemical biographies on an immense scale. They measure the subtle dips and peaks in the starlight that correspond to specific elements like iron, oxygen, and magnesium. A star with a very low iron content, for instance, is almost certainly an ancient immigrant, a refugee from one of those primordial, metal-poor galaxies that was long ago torn apart and absorbed. This process, known as chemical tagging, allows scientists to perform a form of celestial genealogy. They can separate the original inhabitants of the Milky Way from the stellar immigrants, identifying entire populations of stars that share a common foreign origin. This is how we know with such certainty that the stars from the Gaia-Sausage galaxy are truly alien to our own. They carry a distinct chemical mark that sets them apart from the native stellar population. This chemical evidence provides the most crucial proof for the galaxy's violent history. It is not just about finding stars moving on strange orbits. It is about confirming that those stars are fundamentally different, that they were born in a different place under different conditions. Each distinct chemical group represents a different merger event, a separate chapter of cosmic consumption. By counting these groups and analyzing their chemical patterns, astronomers can reconstruct the entire family tree of the Milky Way, identifying not just how many galaxies it has consumed, but also the nature and size of those long-vanished building blocks. This grand narrative of cosmic violence is not a random series of accidents. It is the predicted outcome of how our universe builds its largest structures. The prevailing model of cosmology, known as the hierarchical model, tells us that the cosmos constructs itself from the bottom up. Small objects form first, and they are the fundamental building blocks for everything larger. Our Milky Way is a textbook example of this universal architectural principle. It did not spring into existence as a magnificent spiral. It began its life as countless tiny clumps of dark matter, each a gravitational seed pulling in wisps of primordial gas. These fragments, these proto-galactic building blocks, were the universe's first humble bricks. Over billions of years, they endlessly collided and merged, a relentless process of accumulation and growth. The violent mergers we have been discussing, from the Gaia-Sausage to the ongoing consumption of Sagittarius, are not chaotic exceptions. They are the fundamental, universal mechanism of galaxy growth. This model makes a clear and testable prediction. If large galaxies are truly built from the cannibalization of smaller ones, they should be surrounded by the leftover evidence of their feasts. They should be littered with the debris of their formation, and that is precisely what we observe. The vast stellar halo of the Milky Way, with its rivers of stellar streams and its population of ancient captured globular clusters, is that debris field. The satellite galaxies still orbiting us are the remaining, uneaten building blocks. Every faint stream of stars, every cluster with a foreign chemical signature, is a direct confirmation of this hierarchical process. Your home galaxy is a living monument to a universe that builds through relentless gravitational assembly. This violent cosmic history is not just a story of stars and structures, it is a story about us. The very elements that make up our world and our bodies were forged in the turbulent aftermath of galactic collisions. When the Milky Way consumed another galaxy, it did more than just add stars, it triggered ferocious waves of starbirth. These starbursts created countless massive stars that lived fast and died young, exploding as supernovas and flooding the cosmos with the heavy elements essential for rocky planets. The iron in Earth's core and the calcium in your bones were likely produced in such an event, a gift from a cataclysm that occurred long before our solar system was born. Yet this creative force carries a double-edged sword. A supernova explosion is a cosmic sterilization event, its intense radiation capable of stripping away atmospheres and scorching the surface of any nearby world. For life to emerge and persist, a planet must reside in a relatively quiet galactic neighborhood, far from these periodic outbursts of violence. The gravitational chaos of a merger adds another layer of complexity. As a smaller galaxy is torn apart, its gravity can ripple through the Milky Way, destabilizing the delicate orbits of comets in the outer reaches of planetary systems. This could send a shower of icy bodies inward, a celestial bombardment that might deliver life-giving water to a young planet, or it might trigger an extinction-level event for a world already teeming with life. Our position in the galaxy and the specific timing of our solar system's formation may have been perfectly calibrated by this violent history. We exist in a quiet suburb of the Milky Way, far from the dangerous galactic center, and we formed after the most intense period of mergers had subsided. This cosmic calm may have been the necessary condition for life to take hold and evolve over billions of uninterrupted years. The largest scale events in the universe, the collisions of entire galaxies, may have subtly dictated where and when a tiny, rocky planet could become a home. But how can we possibly reconstruct events that unfolded over billions of years? We turn the universe into a digital laboratory. Astronomers build virtual cosmos from the ground up, not with pixels and fantasy, but with rigorous mathematical code that embodies the fundamental laws of physics. They begin with a vast, simulated void populated by the invisible seeds of dark matter and the primordial gas of the early universe. Then they set the single most powerful force in motion, gravity. With the press of a button, they fast-forward time, watching as their digital creation evolves over eons in a matter of weeks or months. Within these virtual realms, galaxies form naturally. They spin, they drift, and driven by the relentless pull of their own dark matter halos, they collide. These are not scripted animations, they are pure physics in action. The simulations record everything: the formation of tidal tails, the scattering of stars into halos, the creation of boxy bulges, and the intricate patterns of stellar motion. Scientists then perform a cosmic match game. They compare these simulated outcomes, these digital fossils, to the real data we have collected about the Milky Way. Does the virtual galaxy have a thick disk of stars with wild orbits like ours? Are there faint, looping streams of stars wrapping around its halo? Does the pattern of stellar motions in the simulation's core match the peculiar sausage shape we see in our own? When a simulation produces a galaxy that is a near-perfect mirror of the Milky Way, its entire history becomes a plausible biography for our own home. This is how we identified the Gaia-Sausage-Enceladus merger as a pivotal event. Digital experiments showed that a single, head-on collision with a massive dwarf galaxy would produce exactly the kind of stellar chaos and thick disk we observe today. These simulations are more than just videos, they are functional time machines. They allow us to rewind the cosmic clock and witness the violent, creative processes that were, until now, only theories written on a page. They transform the faint ghosts in our halo from mere curiosities into confirmed chapters of our galaxy's epic story. One of our galaxy's most familiar companions is quietly hiding a dramatic secret. The Large Magellanic Cloud, visible as a faint smudge in the southern hemisphere's night sky, has long been considered a mere satellite, a small moon of the Milky Way. But new observations reveal it is far more than that. It is a substantial galaxy in its own right, and recent, precise measurements have uncovered a startling truth. The Large Magellanic Cloud possesses an immense and massive dark matter halo, a hidden sphere of gravitational influence far larger and more potent than anyone had guessed. This discovery transforms its role in our cosmic story from a passive follower into a major gravitational player. As it continues its long orbit around our galaxy, its considerable gravity is no gentle nudge. It acts as a powerful perturbing force, a cosmic tug on the entire Milky Way system. This influence is most strongly felt in the galaxy's outermost regions. The delicate, distant stars of the stellar halo are being stirred by this passing giant. Even the very disk of our galaxy may feel the strain. Astronomers predict the LMC's gravity could amplify or alter the Milky Way's characteristic warp, that subtle bending of the galactic plane, like a ripple moving through a vast spinning plate. This is not a distant, theoretical future. The perturbation is happening now, a slow-motion rearrangement of our galactic structure orchestrated by an object we once thought was insignificant. The ultimate fate of this cosmic dance is inevitable. The same gravitational friction that slows down smaller objects ensures that the Large Magellanic Cloud will one day spiral inward and merge with the Milky Way. It will not be a collision on the scale of the future Andromeda impact, but it will be a substantial event, adding another significant chapter to our galaxy's biography of consumption. This ongoing interaction proves a crucial point. The assembly of the Milky Way is not a story confined to the ancient past. The cycle of interaction and merger continues today, with a familiar object in our sky poised to become the next major ingredient in our galaxy's ever-evolving form. These first stars were cosmic pioneers blazing a trail through the primordial dark. They are classified as population 3 stars, and they were unlike any sun we see today. Formed from the pure, untainted hydrogen and helium of the Big Bang, they contained not a single atom of iron, carbon, or oxygen. This pristine composition had a profound consequence. Without heavier elements to help radiate heat away, these stars could grow to staggering sizes, becoming behemoths hundreds of times more massive than our Sun. They burned at ferocious temperatures, living lives of incredible intensity that lasted only a few million years, a mere blink in cosmic time. Their deaths were their most important contribution. As they exploded in titanic supernovas, the intense heat and pressure in their cores fused hydrogen and helium into the first heavier elements, like carbon, oxygen, and iron. They were the universe's first forges, seeding the void with the raw materials for everything to come, from rocky planets to life itself. We will never directly observe one of these first stars. They all died long ago, but we can find their immediate children. Scattered throughout the Milky Way's vast halo are rare, ancient stars with incredibly low metal content. Astronomers call these stellar relics population 2 stars. Finding one is like discovering a living fossil, a direct descendant of that first generation of cosmic giants. By studying the specific pattern of elements in these ancient survivors, scientists can perform a form of cosmic archaeology, working backward to deduce the mass and life cycle of the long-vanished population 3 star that enriched them. These faint, ancient suns are more than just old stars. They are time capsules from the era of the very first galaxies. Each one is a surviving piece of a tiny, primordial building block, a fossil fragment of the dwarf galaxies that merge to form the foundational core of our Milky Way. Their presence in our halo confirms that our galaxy's deepest roots are woven from the ashes of the universe's first and most brilliant fires. Our galaxy has a varied and complex diet. The Milky Way's growth can be understood on a scale of cosmic consumption, ranging from light snacks to colossal feasts. At one end of this spectrum are the minor, continuous events. The galaxy is constantly nibbling, steadily accreting tiny globular clusters and the faintest of dwarf galaxies. These small additions are like a gentle rain of building material, steadily contributing stars to the vast outer halo without causing much internal disruption. This is the background noise of galactic growth, a slow and steady process that has continued for billions of years. Then there are the more substantial meals. These are mergers with galaxies perhaps 1/10 the mass of the Milky Way, events that leave a more pronounced mark. They contribute significant streams of stars and can cause noticeable ripples and warps in the galactic disk, stirring things up without completely overhauling the system. At the far extreme of this scale are the rare, epoch-defining feasts. The collision with the Gaia-Sausage-Enceladus galaxy was one of these. When a galaxy 1/4 the mass of our own slams directly into the core, it is not a minor event. It is a cataclysm that rewrites the galaxy's entire architecture, puffing up the disk, scattering stars into chaotic orbits, and fundamentally altering its future evolution. The frequency of these events is not constant across cosmic time. In the early, more crowded universe, galaxies were closer together, and these massive, violent mergers were far more common. It was an era of dramatic construction, a chaotic period when the foundational structures of galaxies like our own were forged in a series of colossal impacts. As the universe expanded, galaxies drifted apart, and these gigantic feasts became increasingly rare. The Milky Way's current majestic spiral structure is therefore the integrated result of its entire cosmic menu. It is the product of both the slow, steady rain of small snacks and the violent, transformative feasts of its youth. This layered history is preserved in the different components we see today, a permanent record of everything our galaxy has ever consumed. This hunt for our galaxy's original components is a search for cosmic ghosts. Astronomers are not just looking for the remains of consumed galaxies. They are trying to find the ones that got away, the pristine fragments that have survived intact since the dawn of time. These are not the shredded streams we have discussed, but the original building blocks themselves, small clumps of stars that have stubbornly resisted being torn apart for billions of years. Imagine finding a living dinosaur, a creature from a lost world walking in our own. Discovering one of these proto-galactic fragments would be the astronomical equivalent. It would be a perfectly preserved window into the conditions of the first galaxies, a time capsule from the universe's childhood. What makes these fragments so elusive is their composition. They are not held together by the brilliance of their stars, but by the sheer gravitational might of their dark matter. These ancient clumps are so dominated by this invisible substance that they contain very few stars, making them incredibly faint and difficult to detect against the vast blackness of space. They are like isolated islands in a dark ocean, their few twinkling lights almost completely drowned out by the distance. This is where our most powerful new tools come into play. Projects like the Dark Energy Survey are systematically scanning the deepest recesses of the sky, while the future Vera C. Rubin Observatory will take this search to an entirely new level. Its immense mirror and giant digital camera will be able to detect these faint, ghostly clumps, not by seeing their dark matter directly, but by cataloging the sparse, ancient stars that trace its gravitational outline. Finding just one of these pristine fragments would be a monumental discovery. It would provide the most direct, tangible evidence possible for the hierarchical model of galaxy formation. We would have in our sights a genuine leftover from the construction of our own home, a silent witness that has watched the entire violent history of the Milky Way unfold. The confirmation of these primordial fossils would complete the picture, connecting the theoretical first bricks of the universe to the magnificent galactic cathedral we inhabit today. A galaxy's spin is a fragile, inherited treasure. This rotation, its angular momentum, was gifted to the infant Milky Way by the gentle gravitational tides of the early cosmos, a slow pirouette begun eons ago. But this delicate motion is not immune to the violence of its history. Every major merger leaves its mark on the galaxy's whirl, like a series of cosmic blows altering the spin of a top. The nature of the impact determines the outcome. A direct head-on collision, like the one with the Gaia-Sausage Galaxy, acts as a powerful brake. It can dramatically slow the galaxy's rotation, or in extreme cases, even reverse the direction of the spin entirely. Conversely, a grazing encounter, a sideswipe from a passing galaxy, can do the opposite. It can transfer a burst of angular momentum, like a cosmic push, potentially causing the galaxy to spin faster and with greater fury. The graceful rotation of the Milky Way's disk that we observe today is not its original motion. It is the final, balanced result. It is the net product of every gravitational shove and every braking impact from all the mergers it has ever experienced. This means the current speed and orientation of our galaxy's spin encode a detailed history of its violent interactions. How can we possibly read this history? We look to the stars themselves, sorting them by their age. The oldest stars in the halo and thick disk remember a different time. Their motions are often more chaotic, with orbits tilted and randomized by those ancient, violent encounters. They carry the kinematic scars of the mergers that shaped them. Younger stars like our Sun, born long after the most chaotic periods subsided, trace more orderly, circular paths within the thin disk. Their calm rotation reflects a more settled era in the galaxy's life. By comparing the orbits of these different stellar generations, astronomers can effectively rewind the clock. They can decipher how each major collision tweaked and tuned the galaxy's rotation, adding a little spin here, stealing a little momentum there. The Milky Way's present-day whirl is a palimpsest, a layered record of countless gravitational interactions. It is the final, smooth rhythm emerging from a symphony of cosmic violence. Look up at the Milky Way and you picture a flat, spinning disk of stars, but our galaxy is not perfectly flat. Its outer disk is permanently bent, warped upwards on one side and downwards on the other, like a giant vinyl record left warping in the sun. This is not a static flaw, but a dynamic, living motion. The entire structure is slowly precessing or wobbling around the galactic center, completing a full cycle only once every 600 to 700 million years. What immense force could cause our entire galaxy to flex and wobble in this way? The answer lies in a recent gravitational disturbance. As a satellite galaxy like the Sagittarius Dwarf or the massive Large Magellanic Cloud swings past, its dark matter halo acts like an invisible hand. It does not need to physically touch the stars. Its gravity alone, passing through the outer disk, gives a collective tug on billions of stars, setting them all oscillating together. This creates a vast, slow-moving wave that propagates through the galactic plane, a ripple frozen in time and space. This warp is a profound reminder that a galaxy's structure is not fixed in stone. Even a relatively minor interaction, a cosmic sideswipe from a passing neighbor, can leave a visible, large-scale scar. Our home is not a serene, isolated island. It is a dynamic entity, constantly being reshaped by the gravitational tides of its cosmic companions. This gentle, persistent warp is the galaxy's own memory of a recent encounter, a subtle yet undeniable sign that we live in an active and ever-changing universe. Some stars in our galaxy are cosmic fugitives, racing through the void at speeds so immense they could one day break free of the Milky Way's grasp entirely. These are not ordinary suns moving in predictable orbits. They are celestial outlaws, and their incredible velocity tells a story of violent origins. One group, known as hypervelocity stars, are native to the Milky Way but were violently evicted from their home near the galactic center. Their journey began as a binary pair, two stars orbiting one another in the crowded heart of the galaxy. When they drifted too close to the supermassive black hole, Sagittarius, a star, its immense gravity captured one star and slingshotted the other away at a phenomenal speed, like a gravitational catapult firing a stellar cannonball across the galaxy. This single traumatic event sent the star on a one-way trip into the intergalactic void. But there is another class of high-speed traveler with a completely different story. These are the Intruder stars, and they are not escapees at all. They are invaders, or more accurately, survivors. They originated in smaller dwarf galaxies that were consumed by the Milky Way long ago. When their parent galaxy was torn apart in a merger, these stars were not ejected. Instead, they simply kept the immense, high-energy orbits they were born with, paths that were carved by the gravity of their original, smaller galactic home. Now they soar through the Milky Way on these wild, radial trajectories, permanent immigrants carrying the motion of a world that no longer exists. To an astronomer, these stars are not just points of light. They are puzzles to be solved. By using powerful telescopes to measure a star's precise motion and then tracing its path backward through time, scientists can rewind its cosmic journey. They can follow the trajectory like a glowing ribbon through space, seeing where it leads. Does the path point directly back to the galactic center, revealing a hypervelocity escapee, or does it lead to a point in the distant halo, aligning with the ghostly orbit of a long-devoured dwarf galaxy, marking it as an ancient intruder? Each high-velocity star is therefore a key that unlocks a specific event. A hypervelocity star confirms the violent mechanics at work around our central black hole. An intruder star is a direct tracer of a specific merger, its path a permanent record of the gravitational forces that shaped it billions of years ago. Together, these stellar speedsters add a dynamic and thrilling layer to the galaxy's history, a narrative written not in stillness but in breathtaking motion. Yet the stars we see are only one ingredient in the galactic recipe. A galaxy is not merely a collection of suns, it is a vast reservoir of gas, the primordial fuel for all future creation. While violent mergers scatter stars, they are also master plumbers, installing immense pipelines that channel fresh hydrogen, gas into the galaxy from the intergalactic void. Picture these not as pipes, but as cosmic filaments, vast rivers of dark matter that guide cold, pristine gas flows from the emptiness of space directly into a galaxy's waiting embrace. This steady, silent rain of gaseous fuel is as vital to a galaxy's growth as the stellar rubble from its collisions. It provides the raw material to build new generations of stars long after the initial chaos of a merger has faded. This process introduces a crucial distinction in how galaxies feed. Astronomers speak of dry mergers and wet mergers. A dry merger is the consumption of a gas-poor galaxy, a system that has already used up its star-forming fuel. This adds stars and dark matter, but it does little to spark new life. It is a meal of cosmic leftovers. A wet merger, however, is a feast of possibility. It occurs when the Milky Way consumes a gas-rich dwarf galaxy, a tiny vessel overflowing with pristine hydrogen. This delivery of fresh fuel can ignite a ferocious starburst, a brilliant wave of stellar birth that lights up the galaxy. The balance between these dry and wet events has profoundly shaped our Milky Way's history. Early in its life, it likely experienced more wet mergers, gorging on gas-rich building blocks that filled its disk with young blue stars. As it aged, its diet shifted, with more dry mergers adding to its stellar halo without triggering widespread star formation. This delicate balance between stealing ancient stars and siphoning cold fuel is what allows a spiral galaxy like ours to remain a vibrant, star-forming engine for billions of years. The brilliant disk we call home exists only because our galaxy learned to drink from the cosmic rivers as well as consume its neighbors. These ancient stars are more than just points of light, they are cosmic clocks. By measuring their ages, astronomers have begun to assemble a detailed chronology of our galaxy's violent history, transforming a static map into a dynamic biography. The process relies on a powerful technique known as stellar archaeology. Just as an archaeologist might date an ancient city by the artifacts found in its different layers, scientists date the Milky Way by reading the ages of its stellar populations. The halo, with its ancient metal-poor stars, represents the deepest, most foundational layer. The thick disk is a younger but still ancient chapter. And the thin disk, where our Sun resides, is the most recent and active layer of construction. Each of these components holds stars that were born at a specific time, under specific conditions. By dating millions of individual stars within these regions, and within the faint stellar streams that wrap around the galaxy, researchers can assign a timeline to the mergers that delivered them. The colossal impact with the Gaia-Sausage-Enceladus galaxy, for instance, is now pinned to a pivotal epoch between 8 and 11 billion years ago. This was not a minor event in the galaxy's youth. It was the defining trauma of its adolescence, an encounter that fundamentally reshaped its structure and set its future course. The ongoing, slow unraveling of the Sagittarius dwarf spheroidal galaxy tells a more recent story, one that began its final act several billion years ago and continues to this day. Every stellar stream has its own unique age, a timestamp for its disruption. The faint, pristine GD1 stream might be a relatively recent casualty, while the more diffuse orphan stream could be a fossil from one of the galaxy's very first meals. When you piece all these individual dates together, a grand sequence emerges. It is a chronological list of the Milky Way's most significant meals, a calendar of cosmic consumption that charts its growth from a modest collection of primordial fragments into the magnificent spiral we call home today. This timeline reveals that our galaxy's growth was not a steady, gentle process. It was a story of explosive, punctuated growth, marked by periods of intense violence followed by long eras of relative calm and internal evolution. The biography of the Milky Way is written in the birth dates of its stars, a story of construction that is still being told. Our galaxy's elegant spiral is a cosmic rarity, a delicate form that could only emerge from a specific sequence of events. Across the universe, we observe a spectacular zoo of galactic shapes, from featureless elliptical spheres to chaotic, irregular blobs. This stunning diversity is not a matter of random chance. It is the direct result of each galaxy's unique biography of collisions and consumption. A spiral galaxy like our own has walked a fine line. It has experienced enough mergers to build a substantial halo and thick disk, gathering mass from its companions. Yet it has been spared the catastrophic, head-on collisions with other large, gas-poor galaxies that completely destroyed delicate spiral structures. The specific type of merger is everything. A series of grazing encounters with small, gas-rich dwarfs can fuel star formation and reinforce a disk, but a single major merger with a galaxy of similar size acts like a cosmic blender, violently randomizing the orbits of billions of stars and erasing all disk structure forever. What emerges from that chaos is an elliptical galaxy, a vast, round swarm of stars where no spiral arms can ever form. Our Milky Way's enduring spiral is therefore a historical document. It tells us that while our past was certainly violent, it was not apocalyptically so. We are the product of a specific recipe of mergers, a cosmic diet that built us up without tearing us completely apart. This makes our home not just one galaxy among billions, but one specific outcome in a near-infinite spectrum of possibilities. Its shape a permanent record of a relatively quiet life in a violent universe. This grand family tree of the Milky Way leads to a profound cosmic question. If our galaxy was assembled from dozens of smaller galactic pieces, do any of its original siblings still survive? Astronomers are now engaged in a vast celestial census, scanning the nearby universe for the Milky Way's long-lost brothers and sisters. They are not looking for identical twins, but for galaxies that share a fundamental lineage, systems that formed from the same primordial gas clouds or endured a similar early history of violent mergers. The primary hunting ground is our own cosmic neighborhood, the local group, a gravitationally bound family of galaxies that includes Andromeda, Triangulum, and dozens of smaller dwarfs. The search focuses on specific galactic signatures. Scientists measure a galaxy's age by analyzing its oldest stellar populations, and they read its chemical makeup, looking for that unique fingerprint of elements that suggests a shared origin story with our own. Finding a true sibling galaxy would be like discovering you had a cousin you never knew about, raised in a different town but from the same ancestral stock. This discovery would unlock an entirely new field of science, comparative galactic anatomy. By placing the Milky Way next to a sibling, we could perform a cosmic dissection. We could ask why one galaxy developed a majestic, stable spiral while the other became a turbulent, star-bursting mess. The differences between them would act as a controlled experiment. Did one experience a more violent merger early on? Did it consume its building blocks in a different order? Or was it simply its location in the cosmic web, the specific flow of intergalactic gas that steered its evolution down a separate path? This quest transforms our galaxy from a singular object of study into one data point in a much larger family portrait. It connects the specific, violent biography of the Milky Way to the universal story of how all galaxies grow, live, and change across billions of years. Our home is not just a product of chaos, but a single outcome in a vast spectrum of possibilities. Its unique shape and history waiting to be understood by finding the family it grew up with. Yet for all we have uncovered, the deepest past of our galaxy remains shrouded in cosmic mist. We can count the stellar streams we see, but how many major mergers have truly occurred? Some ancient galaxies may have been consumed so completely, their stars scattered so thoroughly, that their debris is now utterly indistinguishable from the Milky Way's native halo. Their ghostly signatures are lost, blended into the background like a single drop of ink in the ocean. An even more foundational mystery persists. What was the very first building block of the Milky Way? Did one particular clump of dark matter and stars act as the foundational seed, the original anchor around which everything else accumulated? And if so, does the dense core of that primeval fragment still exist somewhere deep within the galactic center, a silent witness to the very beginning? The precise role of dark matter in orchestrating each collision remains one of the greatest puzzles. We see its gravitational effects, but its fundamental nature eludes us, leaving gaps in our understanding of how these mergers unfold on the most detailed level. These are not dead ends, but the very questions that fuel a new era of discovery. They drive the development of immensely powerful new tools, like the Vera C. Rubin Observatory and the James Webb Space Telescope. These instruments will peer deeper into the halo, measuring the motions and chemistries of billions of fainter stars, hunting for the subtlest patterns that betray a completely dissolved ancestor. The story of our galaxy's violent birth is not a finished book. It is a living narrative, one that will be refined, challenged, and rewritten with every new glimpse into the cosmic dark. Our bodies are a living archive of cosmic violence. The iron that carries oxygen in your blood, the calcium that strengthens your bones, the oxygen you breathe with every single breath, none of it was present at the universe's beginning. These elements were forged in the extreme conditions of stellar life and death, a process set into overdrive by the galactic collisions that built our home. When the Milky Way consumed another galaxy, the resulting starbursts created countless generations of massive stars. These stars, in their brilliant and short lives, acted as cosmic furnaces, fusing simple hydrogen and helium into heavier elements deep within their cores. Their spectacular deaths as supernovas then blasted these newly forged atoms out into space, enriching the galactic gas with the raw materials for planets and ultimately for life. This means that a significant portion of the substance you are made of likely originated not in a quiet corner of the Milky Way, but in the heart of a long-vanished companion galaxy during the fiery chaos of its merger with our own. We are, in the most literal sense possible, stardust, but we are more than that. We are the scattered ashes of galactic empires that fell billions of years ago, their remains recycled into our world and into us. This perspective transforms our place in the cosmos. We are not passive observers looking out at a distant and alien universe. We are the universe itself, become conscious, looking back at its own history. Our very existence is a direct and intimate consequence of the grand, dynamic, and often violent narrative that has unfolded across space and time. We are living proof that from cosmic destruction can come the most delicate and profound forms of creation. The serene Milky Way arching overhead is a cosmic illusion, a beautiful mask over a violent biography. Its gentle light is the integrated glow of countless galactic ruins, each star a potential refugee from a long-vanished home. This is the epic saga of creation through destruction, a narrative where cataclysmic mergers are not merely accidents but the fundamental architects of cosmic structure. From the ancient Gaia-Sausage-Enceladus collision that forged our galaxy's thick disk to the ongoing, slow unraveling of the Sagittarius dwarf, our galactic home was meticulously assembled from the consumed remains of others. This entire history is encoded all around us. It is written in the wild, plunging orbits of ancient halo stars, in the distinct chemical fingerprints of stellar populations that should not belong, and in the faint, ethereal streams that wrap around the galaxy like celestial ghost stories. These are not random patterns, they are chapters. As we look toward the future, we see this cycle continuing. The gravitational dance with the Large Magellanic Cloud and the inevitable, majestic merger with the Andromeda galaxy are not distant fantasies. They are the next pages in a story billions of years in the making, reminding us that this grand process of construction and renewal is ongoing. The cosmos is not a static museum. It is a living, breathing entity alive with relentless change. Our galaxy's story is still being written, its final form a mystery that will unfold over eons to come. Let this new perspective settle in. The next time you stand under a clear, dark sky and see that faint, milky band, remember you are not looking at a permanent structure. You are witnessing a dynamic and violent beauty, a celestial battlefield and a construction site, a living monument to the profound truth that from cosmic destruction comes the most magnificent forms of creation.